Hi everyone. So today we're going to look at a little more about capacitors, and specifically we're going to look at series and parallel combinations, and then what is the DC response of the capacitors and how they fit into our existing forms of circuit analysis that we've done so far, which is really DC circuit analysis. So if capacitors are in parallel, as you could see here, I just have two capacitors in parallel, C1 and C2, then what we could see, just like resistors in parallel, is that the voltage across them is the same. So if I look at my VI equations, I could define the current into each one, I1t and I2t. And I1t will be C dV dt, C1 dV dt, I2 C2 dV dt, where the V's are the same. This is this V of t here. So if I wanted to find the total current now, I know that the total current I t of t that I have here is simply the sum of I1 and I2. So this is I1t plus I2t. And if I add these two together, I'll see that this is the same. I could factor that out and I'll get C1 plus C2 dV dt. So I could call this total capacitance, if I'm looking to put this in the form of some capacitance by dV dt, CT will be C1 plus C2. So the total capacitance when capacitors are in parallel is C1 plus C2. Now remember, for resistors, this was the case R1 is equal to RT is equal to R1 plus R2 when the resistors were in series. Here, when the capacitors are in parallel, the total capacitance is the sum of the individual capacitances. So moving on to series, if I have the series arrangement, then I have the current through both of them is the same, right? And the current is the same, or the other way we could look at this is saying the charge stored is the same. So what this means is if I have some charge here, so I have some positive charge here that is going to induce a negative charge on my second plate. This net negative charge could only come from this plate here. That is the only place it is connected, which means I will have the same charge here. So both of these, since they're connected here, both of these will have to carry the same charge. They'll have to store the same charge. If we look at the look at it in terms of voltage and current, since these are in series, the same current will go through both capacitors. So I have now, if I write again my equations, this time I'm going to use the integral form of the equations. I'll have V1 is equal to 1 on C1 integral between T0 and T1 I T dt. This time I don't have any I1 and I2 because the current is the same. And similarly for V2, I'll get 1 on C2. And if I sum these, because the total voltage Vt is the sum of the two voltages, then I'll get the equivalent capacitance here. If I had to write this, it would be 1 on Ct, the integral between T0 and T1 IT dt. So if I wrote it in this form, this 1 on Ct would be equal to 1 on C1 plus 1 on C2. So if I solve for Ct there, if I just make Ct the subject of the formula, I'll get Ct is C1 C2 over C1 plus C2, product over sum, which is the same as we got for resistors in parallel. So we have the converse of the relationships we had for resistors in the case of capacitances. Now, let's look at the DC response of the capacitors. We know that Vt is equal to 1 on C integral of It dt, or It is equal to C dV dt. If we have a DC, it means that the rate at which the voltage is changing, dV dt, is equal to 0. Since V is a constant, remember for the DC circuits, they were not functions of time. When we wrote our equations, there was no time in it. And that's because with DC, everything settles down to a constant level. So now the rate of change of voltage in steady state will be 0, which means the current will be 0. And what did we come across that has a 0 current through it? It's an open circuit. So in steady state, the capacitor behaves like an open circuit. Now what this means is that if we are solving a circuit with a capacitor in it and we're looking at the steady state response, and the steady state response means the levels of the voltages when everything settles down and become constant, so they are steady, the circuit is in a steady state. What it means is that we could simply replace the capacitor with an open circuit. So if I had to solve, say, for the current through RL, I would be able to, and I had this circuit to begin with, I would simply replace this with an open circuit, get to this point, and then I could simply say 10 volts divided by 10 ohms is 1 amp. So if you have DC circuits with capacitors in them, that is what you need to do. You simply replace the capacitors with open circuits. And one important, very important thing to remember is that this is true only when the circuits are in steady state. So you'll notice we have no switches here. Later on, we will look at what happens when we introduce switches and what is the transient response of the circuit. That is before the circuit settles down. How does it behave? So, in summary, we just looked at how we derive the equations for the parallel and series combinations of capacitors, and we looked at solving steady-state DC circuits with capacitors in them. Next time we'll start looking at inductors, the basic operation, and then the series and parallel operation as well.